Whenever massive tech giants like Facebook or Google suddenly just vanish from the internet for a few hours, the culprit almost always turns out to be a BGP error. I mean, BGP is essentially the duct tape of the internet, right? So let's dive right into this explainer. We're going to break down the exact mechanics of BGP path advertisement. If you've ever wondered how on earth all these completely disparate networks across the globe actually agree on routing all that traffic, well, you're in exactly the right place. We're going to take our source material and build a really clear, conceptual model of how routers actually talk to each other to make the modern internet work. We've got a ton of routing logic to cover, so we'll just follow this roadmap right here. We're going to take this whole complex process chronologically, step by step. So 1, meet the autonomous systems. 2, the setup and handshake. 3, exchanging maps. 4, populating tables. 5, forwarding traffic. And finally 6, monitoring the session. Obviously, to understand how the internet connects, we first need to meet the entities doing the connecting. So section 1, meet the autonomous systems. An autonomous system, or an AS as it's commonly known, is basically an independent neighborhood on the internet. It's a network, or maybe a group of networks, operated by a single organization representing a completely distinct routing domain. Now, they manage all of their own internal traffic beautifully, but without a connection to the outside world, well, an AS is essentially just an isolated digital island. To be a functional part of the wider global internet, they absolutely need a robust, reliable way to talk to outsiders. Imagine two totally distinct neighbors in this digital city. On the left, we have router A1 representing organization A, and sitting right across the street is router B1 representing organization B. And they've got their specific IP addresses too. AS1 operates at 192.168.1.1, and AS2 is directly accessible at 192.168.2.1. These two routers, they're basically our main characters today, as we watch them figure out exactly how to communicate with each other. All right, let's move right along to section 2 and see how this builds from the very first connection between these two neighbors, the setup and handshake. Now, before we throw a bunch of complex IP addresses into the mix, just take a look at these 4 fundamental steps. Think of this as our core playbook. It's what the routers are going to execute to build their digital highway. Step 1, establish a BGP session. Step 2, advertise route prefixes. Step 3, select the best path. And finally, step 4, forward packets. Literally every single piece of data we look at next is just executing this really elegant 4-step cycle. Okay, so the absolutely crucial point here is that the initial BGP session handshake happens directly over the specific IP addresses of our two routers. Before any grand maps are shared whatsoever, router A1 reaches out to router B1 using those exact IP addresses we just talked about. And why do they do that? Well, because this direct IP-to-IP connection establishes deep trust. I mean, they have to verify exactly who they're talking to and confirm the connection is totally secure before they start, blindly accepting routing directions for potentially sensitive traffic. So they are officially shaking hands. And once they're formally connected and that trust is established, it's time for our routers to share what they know. Section 3, exchanging maps. What's really fascinating here is that each organization has a specific network block, or a prefix, that they desperately want the other one to know about. This is literally them trading their internal maps. AS1 basically announces, hey, I am responsible for the 192.168.10.0/24 neighborhood. And meanwhile, AS2 chimes in and says, good to know, I'm responsible for the 192.168.20.0/24 neighborhood. They're explicitly putting their territories on each other's radar so the traffic actually knows where it can legally go. But it's not enough to simply say a destination exists. You have to tell your neighbor exactly how to get there, right? So during this route advertisement phase, they send these specific BGP update messages, and importantly, they declare themselves as the next hop to reach those specific prefixes. Like, notice how router A1 advertises its prefix, but then importantly, it appends its own IP as the next hop. And router B1 does the exact same thing. They aren't just handing over a map, they're pointing to the exact door you have to walk through to enter that territory. Now, the routers don't just blindly accept this data. Actually, they process these updates through a BGP route selection algorithm to ensure they are picking the absolute best path. I mean, sure, in our isolated 2-router scenario here, the choice is pretty straightforward. But think about the real world for a second. The global internet routing table actually has nearly 1 million distinct paths. 1 million! This algorithm is the powerful brain that literally has to sift through all of that noise to find the absolute most efficient route. And it does it in a matter of milliseconds. So after calculating the best path, they actually have to write down the results to make them permanent. Let's look at Section 4, Populating Tables. When populating their tables, router A1 securely logs organization B's prefix, that's the 20-dot network, and it strictly associates it with router B1's IP as the next hop address. And of course, router B1 does the exact same thing for organization A's 10-dot network. This is really the tangible result of all that communication we just talked about. It's basically the equivalent of saving a new contact and their home address in your phone, just so you never have to look up the directions again. Their routing tables are fully primed and they are ready for action. So, with the routing tables officially updated, the maps completely exchanged, and the session fully established, we finally arrive at the most important question for any network. How do packets actually move now? Well, it's time to put our newly minted routing paths to the test. Let's move to Section 5, Forwarding Traffic. Thanks to everything we literally just covered, the actual movement of data is now completely seamless. When, say, an email or a high-definition video stream destined for organization B hits router A1, it just references that newly populated table, sees that the required next hop is 192.168.2.1, and it flows effortlessly to the correct router. And obviously, the exact reverse happens for any traffic returning. That theoretical handshake we started with has officially transformed into a highly functional data highway. But of course, network administrators need to make absolutely sure this vital connection stays healthy over time, which brings us to our final section, monitoring the session. Administrators can run the Show BGP Neighbors command to monitor the active session and verify that route advertisements are continuously exchanging. And honestly, this step is absolutely critical. Because think about it, if this session just silently drops and nobody notices, traffic meant for those prefixes suddenly black holes into absolute nowhere, and end users completely lose their connection. This command basically allows an admin to look under the hood and confirm that the handshake we just spent all this time building remains totally resilient. As you reflect on the foundation we've built in this explainer, just take a second to consider the massive scale of these micro-interactions happening every single second to keep the world connected. I mean, if this incredibly detailed multi-step interaction is required just to get two routers to agree on a path, how absolutely staggering is the complexity when millions of these updates are happening simultaneously across the global internet? It's a continuous, totally invisible digital choreography. Definitely keep that in mind the next time a web page loads flawlessly on your screen.